Okay, so thank you. So I'm not going to talk about inheritance. I'm going to talk a lot about types. So it's, in a sense, the dual of Andrew's talk. And you'll be the judge whether it's minimal, or it's a small calculus or not. So a long time ago, in a galaxy far, far away, there was this paper. And it's really been a long time ago. And all of us has changed places. Two of us have changed continents since then, and the other has changed coasts. So it's been a long time ago. But basically, what I've been working on was always about that in one way or another. So what then was proposed was that languages should have both virtual types, and some languages they're called abstract types, and type parameters, because they are both of them have advantages that the others don't have in some situations. And what I want to show here now is that actually, no, it's all virtual types. So virtual types can be a basis for both parameters and abstract types, and they have a beautiful type theoretic foundation. So our aim is to provide a minimal theory that can model type parameterization, modules, objects, and classes. Let me just get this. Okay. With minimal, one of the consequences of minimality is that we are not going to deal with inheritance. If you want inheritance, then you will need an encoding. There were several attempts of that before, including one of which I was a part, that was New Object, which was proposed as a basis for Scala in 2003. But I think it's fair to say that none of these approaches felt completely canonical or minimal. I remember still that after the ECOP talk, I went to Martina Buddy, who was in the audience, and said, "What did you think of it?" And he said, "Yeah, well, it didn't really feel super canonical. It doesn't think it's the last word of the thing." And that really made me think, and that basically the end of this thought process is what you see here in this talk here. Also, I should mention 1ML, whose goals are related. So 1ML can model type parameterization and modules, but in a sense it goes the other way. It maps everything into system F, whereas we map also system F into a combined calculus that can not just do modules, but also can deal with subtyping and thereby model objects and classes. So not everybody agrees with this aim to combine object-oriented functional programming. In fact, in reality, a lot of functional people see object-oriented programming like this one, like in the film Office Space, the evil boss that imposes stupid design patterns on you. And a lot of object-oriented people see functional programmers as these crazy scientists who are crazy and, in the worst case, dangerous. And the Scala community has found itself at a sometimes uncomfortable position between those two extremes. Sorry? You mean this? That looks more like him, yeah. So what we're going to go into now is dependent types, because we want to model modules, and modules have type members. So modules will be objects with type members. That requires a notion of dependent types, because the type referred to by a type member depends on the owning value. It's a field of the object, so to speak. In Scala, we restrict such dependencies to paths, which is essentially an immutable value followed by selections of immutable fields. But here I'm going to restrict it further to just variables. So an object reference is a single variable. So just before we go into that, I want to give you some taste of how this does look like in a program. So here's a type you probably know well, heterogeneous maps, so type-safe heterogeneous maps. So the way we do it here is we have a trait key that has a type member value, and that's all it has. And then we have our HMap, our heterogeneous map has a get method, which takes a key and gives you back an option of the value type in the key. So you can have maps with keys of several types, but you know that the value will match the key. And add takes a key and a value of type key.value, and it gives you back an HMap. So here type value is an abstract type declaration, what I called virtual types at the beginning of the talk. And key.value is a path-dependent type because the type depends on this variable key, the parameter key here. I can go further with the example and just add two keys, let's say a sort key, which is a sort option in a command line where the value would be string, and a width key where the value would be int. And then I could say my parameters of the command line is hmap.empty, so an empty map, and then I add the width field with value 120, and I add the sort field with value time. But I couldn't add, let's say, the width field with value true. That would give me a type error, because true is not does not correspond to the value field in the width type parameter. So that's a way to program with these types. It can be done with type parameterization as well. So in that sense, the example is too small to show off the advantages of doing it that way. But I guess you will agree that it's a nice, simple way to express these things. Virtual types can also model type parameters. So that's what I'm going to show you next. So I'm doing this with the canonical example, which is just cons lists. Here's a way we could write cons lists in Scala if we simplify it a lot. So we would have a base trait called list of t. It's parameterized with the type t, and then it has these three fields: is empty, head, and tail. So is empty is of type head is of type t, and tail is of type list of t. And then we have two constructors, which are both methods in this case: nil, which gives you the empty list, where is empty is true and head and tail are undefined, and cons, which gives you a cons cell. So all this is completely canonical. It's one simple way to write this in Scala. So how would I encode that with virtual types, just to see the example? Well, what I would need to do is I would say, well, list is now no longer parameterized, but the type parameter t became a type member here. And the tail thing then is not a list of t, but it's a list where the type t is the same as the current the type t of the current list. So t equals self.t. Self here is essentially the reference of this in the list. So I choose here to give it an explicit name, which is a possibility you can do in Scala. Okay, so nil then would do the same thing. It would create a new list, and it would say, well, the type t now is the type parameter x, and is empty is true, and since I don't have triple question marks, which gives an exception in this simple thing, I just treat it as an infinite recursion. Common trick to model errors as just non-termination. And cons then would take, again, a head of type x and a tail where now I get a list where the type t must be the same as this x, and again, I have this construction here. Okay, there's a slight variation because in actual fact in Scala lists are covariant. So that means if a list of fruit, let's say a list of apple is a subtype of a list of fruit, because apple is a subtype of fruit, that's expressed with this little plus sign here. So with covariant lists I have a slightly different encoding. Well, first there's an advantage to covariant lists, and that's that I can write the value nil as a single value. It doesn't have to be parameterized because I have a bottom type called nothing, and so a list of nothing is a list is a subtype of a list of an arbitrary type. So a def can become a val. The encoding you see here, the encoding is pretty much like what I had before, but instead of equal signs I have upper bounds. Now I say here the type t in tail here and here. It must be a list whose element type is a subtype of the type of the list that I have here. So let's say I have a list of apples and a list of bananas. Then the result of what I create can be a list of fruit. So the tail, the list of bananas, is the type t is a subtype of the type of what I create here. So instead of a type equality, I have a subtype sign. And the same thing here where I do it here. Okay, this is all Scala. So this is all Scala code. That's just to show that I can do this translation in Scala itself. So I have this available already now. But of course, you could say, well, that's actually a lot less convenient than type parameters to write in most of the cases. So we want to keep type parameters in the language. But essentially the benefit that we gain from this work is to say, well, type parameters are a derived feature. We don't need to, they don't need to be primitive. Okay, you could say, well, no, you still have some type parameters left, like that x here, but we can get rid of them as well by just saying, well, let's make a type param box that contains a single field, call it type, capital type, And then instead of a polymorphic function, I have a dependent function, a current dependent function. So it first takes not a type, but a type param, a type box. And then wherever before I refer to t, and I'll just refer to t.type. So that's that way I can model polymorphic functions as dependent functions. Because I have to put the type in a box. Yeah, that's right. Yeah. Again, it's an encoding. It's not what I propose actual programmers will do. Yeah. Okay, so let's try to develop a model for that. A model that's maximally simple. That's at least I would claim a sort of a local optimum of models for this sort of things. So what we need to do is we need some way to write dependent functions. So here we have a lambda, and I choose the for all type for that because I never got the hang of product types, dependent product types. Found it very weird that a dependent sum is really represented as a product, and a dependent product is represented as a function. So I just want to keep these for alls, which are the same as in system F. But now, of course, the quantifier is not a type, it's a variable. It's a term variable. So that's the crucial difference here. And we also need a way to write objects. So an object is written like this. It's a new, and its type is that thing here. So the object definition, think of that as just a new, where I have some definitions, and that's a type of self, and that's the name of self, and that's its type. And its type is a recursive type. We're going to see that in a second. So an object then, it's composed of a self-reference, so that's essentially the name of this, and that's its type, the type that I assume, and a body of definitions D. And definitions are as simple as could be, so I can define a parameter-less method, so A equals T. I could call this a by name field, it's the same thing. The important thing is the right-hand side can be an arbitrary term, so it's not evaluated. And the type of that is then written the same field name, colon, its type. Or it could be a type field, which is just a type alias. So that's a type label, that's a type. And its type is the same type label, and then we have an upper and a lower bound. To represent the alias information precisely, the upper and lower bound would then be both type T, so that's the same as a type alias, but they can be different. So that way we essentially get intervals of possible types. And I combine these definitions with intersections, and their types are pure intersection types. So I just intersect the types. And as usual, objects decomposition is selection, so I can select a term label and a type label. So object types then, they are these recursive references. So before explaining it a lot, I think it's probably best to just look at it as an example. So we had this type of lists. That was this thing here, this trait. So how would I, no, sorry, I want to get the encoding. So that one here. So how would I represent that in the proposed model? So here's how that would work. I would say, well, I have a type label list, and it has a lower bound of bottom and an upper bound of this recursive thing. So the recursion goes over the name of this, call it self, that name is arbitrary, and it has 4 definitions. One is there's a type T, whose lower bound is bottom, and upper bound is top. There's the isEmpty field, there's the head field, and the type of the head now, that's the recursion here. It's of type T, self.t. So that's where you get the recursion here. And likewise, sorry, that should be tail, that's a typo. That's, again, this type that you see here. So that's what these recursive types are. They're really essentially the body, and the variable is just a way to essentially recurse over the this of the type. That's the essence of the open recursion that you have in object-oriented languages. That thing should be tail here, and its type is list. So that's this thing here. Good point, yeah. So it's all turtles all the way down. So in a sense, list must be a member of a package that gives you the list functionality, and it has its own self, and I really should have written the self of that package list, but I didn't want to go that far. So for the moment, I just give you list a priori. But the paper contains the full development starting from the root objects to everything. So if you look at the paper, you'll see the correct encoding. Because list is not a member of self. Those are the members of self are T, is empty, head and tail. Because self is a term, it's not a type.
Is there a type?
That should be tail here. Yeah, that should be tail. Yeah. So the self is just what you would write as this in an object-oriented language in Scala or Java.
So what's the minimal you need to add to this?
A well-typed?
Sorry, so what you've written here, you say, oh, well, I elided some stuff.
Yeah.
Right, because that would make it messier.
No, it doesn't make it messy. It just means I have to produce more code. I have to start from the start and have to say, well, my root package contains a list package which contains a self which defines this list thing. So
could I talk about? Can you write out something? So root is like the whole bloody system.
Right. Yeah.
Right.
Yeah.
I would like you to talk about lists in isolation from the whole bloody system.
Yeah, I can do that.
Right. What would that look like?
That's a let. I use a let. We will see that in the syntax. I can define a list package by its own using a let, and then essentially I just select it. But whenever I need list, I really have, let's say the package is called collection, because list is a listing collection. And I can never write just list. I always have to write collection, which is a value, which I might have in scope through a let, and then collection.list. But basically, if you look at Java and Scala, it's the same thing. So you get stuff out of packages, and I would argue packages are values. So they are essentially values that contain, they're basically a special kind of objects that contain members that are represented by files. Yeah. Okay, cool. So we need subtyping. Oh, and people will say subtyping is evil. But here it's actually essential. It's essential. Why? Well, because we have these nominal types like self.t. And now we have to say, well, what is it? Does it have an alias? Does it have an upper bound? Does it have a lower bound? And all these things are provided by subtyping. So we need subtyping to essentially relate nominal types like self.t with essentially what the information that is in that type. So subtyping is essential here. Okay, so let's go right into the calculus, and I want to just convince you how boring it is, because there's not really that much there. So we already went through the syntax, so essentially that's the whole syntax that we have here. The term language is super simple. We just have variables. The values you've seen, objects and functions, selections, applications, and let. That's all we have. And I will simplify further and say this whole thing must be in ANF form, which happens to be a good fit with essentially the variables as prefixes, and it's a fairly insignificant restriction. I could extend it to the full thing, adding more rules, but I think philosophically ANF is the right fit for this thing. Okay, so evaluation. So that brings us to another paper. That was the first paper I collaborated with Phil with. That was the call by need lambda calculus. We talked yesterday about that. And that had a funny notion of evaluation, which I have also stolen here for this treatment. So the evaluation in that thing is a small step evaluation relation. And it has to deal with lets in some way. So essentially, where other people would use a store, I use essentially a prefix of lets, and then I somehow have to relate what's in the let, that x is a certain value, with something where the x gets used. And that usage point has to be in evaluation position. So I use evaluation contexts for that. And in our system, an evaluation context is just, I can evaluate at the top. I can evaluate at the top of a let, of the left-hand side of a let, or I can evaluate inside the right-hand side of a let. So that's my evaluation context. So here I say, well, if that's in that position, then, and furthermore, the value here happens to be a lambda, a function, then I replace the value by the right-hand side, where the actual argument replaces the formal parameter. So that's just the usual beta reduction rule. And the dual rule here is for selection, where I say, well, if I have a let, and in the let I have a selection, then I replace that by essentially the right-hand side of that selection. So if the selection defines a field labeled A, and its right-hand side is a T, then I will replace the selection with that T. And the other two rules are administrative, where I say, well, I will shortcut variables. If x equals y, then I can just do it with a variable substitution. And the further thing is the last rule bubbles out nested lets. So if I have the right-hand side of a let is another let, then I will flatten them like this. We had that same trick already in the Call-by-Need paper. It's exactly the same treatment. I do rely on nested let. Sorry, maybe I got that wrong, that a normal form doesn't let you do that. Yeah, so here, it's extended a normal form. Yeah. Okay. Right. Okay, so that was the operational semantics. What about the types? So that's essentially the type assignment rules, and essentially I just want to convince you that they're all completely standard and boring. So let's take the first two. That's just a completely standard rule for dependent function types. So I give you that rule here, and it's the boring elimination rule again for dependent function types. And here it's essentially the nice thing about ANF is that essentially I can only substitute things that are valid prefixes. I don't need to have to deal with the fact that I have terms. The other nice thing for the whole thing is I never have a notion of substitution, only variable renaming. So this calculus does not need substitution. The only thing it needs is variable renaming. Okay. Other boring rules are, that's the rule to create an object. So here I say, well, I've already given the type of the object in the new. I only have to check that the actual definitions have that type. And then in that case, I get a recursive type. And the selection rule couldn't be simpler, but it says, well, if an object has this type, then the selection has the field type. Then you could say, well, how do I get from a big object type like that to that? We'll see that that's subtyping that will do that for you. Okay, yeah, I'll try to speed up as fast. Okay, the last rules are substructural rules where I say recursive types introduction, elimination, and introduction. So recursive type introduction says, well, if x has a type t, then x has the same type as recursively xt. So essentially, I have here a reference to in t that can refer to the value x. It can be recursive by referencing an environment value, and here I just lift that into a recursive type. And that rule is reversible. So if something has type recursively xt, then it has also type t, and here it's essential that that x and that x are exactly the same name. So I rely on alpha renaming to get there, otherwise I would have to give you a substitution for this thing. So essentially what I say, well, it doesn't matter whether I refer to an x in the environment or that is of this type, or whether I can say it's the type and the x is my own recursive instance. It's sort of the external view of an object, it's this object x, or the internal view of that object sets to this, and if I know that the two are the same, then I can make use of that in types. That's the standard rule of the lambda calculus with intersections, so don't think I need to say more about that, and that's the standard subsumption rule. So that's it. Definition type assignment, we can skip. We've basically already seen that just says, well, what kind of definitions have what kind of types, completely straightforward. And the last thing is subtyping, where the left column is again completely standard. So that's just the reflexive, transitive, bottom, top, and the natural rules for intersections. And the right-hand side is also pretty standard. That thing just says, well, if we have x, which is essentially has a type member with lower bound s and upper bound t, then x.a is a subtype of its upper bound and a supertype of its lower bound, of course. And the other rules are just the structural rules, which say, well, how do I essentially compose definitions here and here, where for the type intervals, I have the contravariance in the lower bound, of course, and the same thing is for the dependent functions, and again, I have the contravariance in the lower bound and the covariance in the upper bound. So these are also completely standard. Okay, so you say, the takeaway I want to give you here, this is completely boring. This is completely standard. There's nothing really much to be seen. Also, I should say there's no trick here. There's no superscript, subscript, overbar, or things like that. They're just plain symbols, very simple formulas, every one of the typing rules. The surprising thing was that you should say, well, it should be completely easy to prove that with all the things that we have developed so far. The surprising thing was it took us 8 years to prove the soundness of this calculus. So basically we started 2008, and many of postdocs despaired on the task. So we had some previous publications, notably in Fool in 2012 and in UPSA 2014, which reported about some advantages and, I guess, until then, lots and lots of difficulties. So the essential challenge, why it's so hard, is that that calculus does something that very few others do, namely that it essentially gives you a theory that's programmer definable. So what do I mean by that? So as we've seen, the subtyping relation in Scala and in dot is given by user-definable definitions. So here's the Scala definition, that's a dot definition. Both make T a supertype of S and a subtype of U. You've seen the rules. So by transitivity, S is a subtype of U. And that's something that doesn't hold necessarily. So the type definition above proves a subtype relationship, which was potentially not provable before. And that can get you in trouble. So you could then, for instance, have a type definition like this. T is a supertype of any and a subtype of nothing. The same argument as before, that means any is a subtype of nothing. So top is a subtype of bottom. And by transitivity, that means that every type is a subtype of every type. The subtype relationship collapses to a single point. Now, why is that bad? Well, it's bad because once you have that, you can't prove anything anymore. So in particular, the simplest inversion lemmas fail. So let's say you have a binding here. X is an object type. And in the corresponding environment, then we would have a binding that X is the recursive type. Okay, so what we'd like to do is to say, well, if you have a recursive type like that, then X must be an object, because a recursive type, that's a type of an object. But because every type is a subtype of every other type, X could also be a function. We just don't know. And that means we do not know whether we can prove preservation. Okay, so can we exclude bad bounds statically? So that would be the thing that, for instance, in an ML module system, you can essentially throw bad programs out immediately because everything is stratified. Every definition follows definitions that come before. In Scala and in dot, unfortunately, no. And that's because of type intersection. So take these two types. In S, type A is unconstrained and B is between A and bottom. And here A is between top and B is unconstrained. Individually, they both have good bounds. The bounds are satisfiable, but the intersection does not. So if you take the intersection, then because it propagates into the fields, you get this thing here. You get that essentially A is a supertype of top and a subtype of bottom, and the same thing for B. And it turns out that even if you did a non-modular program analysis and checked every intersection in your whole program, would still be not enough because of subsumption. These things can actually arise at runtime potentially. So how can we deal with it? Well, the crucial observation here is that we need to reason at the top level when we want to prove observation only about some particular kinds of environments. Namely, they correspond to evaluated left prefixes. And those prefixes bind variables to values. And we know that in a value, we have good bounds, because in a value, in an object value, all types have aliases. And so they have a good bound that's T to T. So that's their alias. So we have this crucial distinction that we say under a lambda, where we can deal with arbitrary types, we can say nothing. But during evaluation in a value, we can actually achieve that. And the paper provides an elaborate argument how to make use of that observation for the full soundness proofs. So that's what... Sorry? Okay, yes, exactly. So there have been some variants, which I should mention before finishing. So the first soundness proof was by Tiark and Nada, and that contained a big step semantics for a variant of dot. That variant was more powerful because its meta theory also dealt with subtyping between recursive types, which we decided we don't want and we don't need here, because we essentially only need to deal with subtyping between nominal types, so we don't want to deal with structural recursion here. The paper that at Wadlerfest presents an independently developed proof that uses the small step semantics that you have seen, and I think we took heed of Phil's advice here of the importance of being stupid. To conclude, I hope what we've achieved is this, that we essentially can look onto the beach and have a nice combinations of functions and objects, and there's no conflict anymore. Thank you.